Hello students, welcome back to online classes. In last video we discussed about the S block elements, that is group 1 and group 2 elements, and the properties of the alkali metals like electronic configuration, atomic or ionic radii, ionization enthalpy, and the hydration enthalpy. So next is the S block elements, means the alkali metals are giving the characteristic color whenever they are exposed to oxidizing flame. So the alkali metals will give a characteristics color to an oxidizing flame. Because in case of alkali metals, the outermost electron, means the NS1 electron, it is loosely held. Whenever it is exposed to oxidizing flame, it will absorb the heat energy and it will enter into the excited level. As a result of that, it is unstable in the excited state, then it is come back to the ground state by emitting the radiation. So whenever the electron which is present over the surface of a alkali metal, so this is, let us imagine, so this is the surface of alkali metal. So when you are providing the heat energy, or when you are going to expose these alkali metals to the oxidizing flame, they will absorb the energy, and from ground state to it is undergo excitation and enters into the higher energy level, or else excited state. So at this state it is unstable in nature, and again it will come back to the ground level. So while coming back to the ground level, it should emit the radiations. So these radiations are visible in the visible region. So these radiations are available in visible region. So that is why they will impart color. So by the help of this flame technique, we can identify the different alkali metals. So lithium will give crimson red color, the potassium will give violet or a lilac color. So in this way, all alkali metals are giving different color whenever they are exposed to or impart to oxidizing flame, and these radiations are visible in the visible region. So that is why they will give different color. So this will identify by the help of a flame photometry technique, or else a flame spectroscopy technique. So we will write the different colors shown by the different alkali metals. So lithium will show crimson red color, so this is the metal and this is the color of the emitted color, and next it is the wavelength. So at a particular wavelength we will observe this kind of a color here. So 670.8 nanometer. So next the sodium will give yellow color at 589.2 nanometer, and potassium will give violet color at 766.5, and rubidium will give red color, and sometimes we will also observe red violet color mixed at 780, and the cesium will give blue color at 455 nanometer. So lithium will give crimson red, sodium will give yellow color, the potassium will give violet, rubidium is red, cesium is blue. So all the alkali metals are showing different color by absorbing particular wavelength. At a particular wavelength they are giving the colors. So that is why it is very easy to identify the alkali metals by the help of flame test or else flame photometry. So in this way the alkali metals are giving the characteristic color to an oxidizing flame. So this is because the outermost orbital electron will absorb that heat energy and enter into the excited state, while coming back to the ground level it will emit the radiations. So those radiations are responsible for the color of alkali metals. So those radiations are responsible for the color of alkali metals. So that's why alkali metals will give the different colors. So these alkali metals are white, softer and light metals. Because of the large size, these elements have low density which increases down the group, that is from lithium to cesium. However, the potassium is lighter than that of the sodium, and the melting and boiling points of the alkali metals are low and indicates weak metallic bonding. So the alkali metals are showing low melting point as well as the low boiling point because metals have low melting point and low boiling point. Because these have weaker metallic bonding. Weaker metallic bonding. So if metal bonding is loose or weaker, it is very easy to break that bond with the low temperature. So that is why those metals will exhibit low melting point as well as the low boiling point. If the bond is stronger, then they require high amount of heat or high amount of temperature to break down the bond. So those compounds are showing high boiling points as well as the high melting points, but these alkali metals are having low melting point and low boiling point because they should have weaker metallic bond. So that is why the melting point or boiling point is decreases from lithium to cesium. So these are the some physical properties of alkali metals. And the potassium and cesium, those are useful for the photochemical cells. Those are using as electrodes because they are showing the flame technique. So next is the chemical properties of alkali metals. So these alkali metals are reacting with many chemical compounds like water and air, oxygen, halogens, etc. So that is why the chemical properties of alkali atoms are important. Chemical properties. So in the first one is the reactivity towards the air. Reactivity towards air. So when the alkali metals are tarnished in dry air or oxygen, they will form their corresponding oxides. When the alkali metals are exposed to or tarnished in dry air or oxygen, they will form oxides, and these oxides are react with the moisture. So moisture is nothing but water molecule which is present in the atmosphere. So this will react with the moisture, they will form hydroxide. Firstly, the oxides are formed whenever alkali metals are tarnished in dry air. After reacting with the moisture, they will form the hydroxide. So these hydroxides are undergo further composition. So firstly we can say that the alkali metals furnish in dry air or oxygen to form their oxides. Dry air or oxygen due to the formation of their oxides. They react with oxides which in turn react with moisture and forms their hydroxides. And these alkali metals, they form oxides, peroxide as well as the superoxides. If metal with O is considered to be metal oxide. So if two metals are coupled with two oxygen atoms, then those are considered to be peroxide. If one metal is presenting two oxygen atom, then those are said to be superoxide. So metal with one oxygen will give oxide. Two metal with two oxygen atoms will give peroxides and peroxide. And one metal with two oxygen atoms will give superoxide. Okay, this is the difference between oxide, peroxide and superoxide. So one oxygen is oxide, two oxygen peroxide, two oxygen with one metal is a superoxide. So lithium forms monoxide, sodium forms peroxide, and other metal will forms the superoxides. And usually in all these, the oxidation state of alkali metals should be +1. So I will write this. So the lithium, if it is exposed to air, it will give lithium oxide. So only one oxygen is there, so that is what it is called as lithium oxide. Next, the sodium. This forms both oxide as well as the superoxides. So whenever sodium exposed to oxygen or react with the air, it will form the sodium superoxide, Na2O2. Sodium superoxide. And again other alkali metals like potassium, cesium, if they react with air, they will form the corresponding hydroxide or oxides. Okay. So here metal may be potassium, rubidium, cesium. So when metals react with oxygen, they form the corresponding superoxides. In all these oxides, the alkali metals are present in +1 oxidation state. The lithium shows the extensional behavior and it is react directly with the nitrogen and gives the lithium nitride. So all alkali metals in their oxide form, they will exhibit +1 oxidation state, and the lithium shows some exceptional character. So that is, the lithium, it will react with the nitrogen which is present in A and gives the lithium nitrate. So the lithium is reacts with the nitrogen present in A and form lithium nitrate. Means it is very reactive. Lithium is very reactive and forms lithium nitrate. So this nitrogen is present in the A. So that will give the lithium nitrate. As a result of that, the alkali metals are stored in kerosene. So we have stored these alkali metals in kerosene because of their highly reactivity towards the air and water. So we will get alkali metals in a kerosene oil because of their highly reactivity. High reactivity towards air and water. So simply, if you have kept or exposed the alkali metals to air and water, they vigorously show reaction. So sometimes these are also act as explosives. So that's why, to avoid that kind of dangerous situation, we are storing alkali metals in the kerosene oil. So this is about the reactivity towards the air. So they should form the corresponding oxides and hydroxides when their reactivity shows towards the air. So next is the reactivity towards the water. Second chemical property is reactivity towards water. So when the alkali metals, if they are reacted with water, they should form corresponding hydroxide ions. 2OH with the liberation of dihydrogen. So when alkali metals reacts with the water molecule, they form the corresponding hydroxides with the liberation of dihydrogen, where M may be alkali metal. So any alkali metal. So and here the lithium has most negative electrode potential, means E minus is negative 1, and its reaction with water is less vigorous compared to others. So lithium has most negative E minus values, means potential values, and it will show lesser reactivity towards the water compared to that of sodium. It will not react with water. Vigorously compared to sodium. But other than comparison, lithium also shows vigorous reaction with water. But when we are comparing with sodium, it is somewhat lesser because it has negative E minus. So this behavior of lithium is considered as this behavior of lithium is mainly due to its smaller size and ionic radium. So as a result of that, it will show high hydration energy since the lithium has has smaller size and maximum hydration enthalpy. Maximum hydration enthalpy. So this is the reason. Okay. So other metals of alkali metals, they will vigorously react with the water, and these also react with proton donors like ammonia, alcohol and alkynes. So these alkali metals, they will also react with the proton donor also react with proton donor molecules like alcohol, alkynes and liquid ammonia, etc. So in this way they will show reactivity towards the water. When they react with water, they form corresponding hydroxides with the liberation of hydrogen, and lithium has most negative potential, since whenever we are comparing with the sodium, the lithium shows lesser reactivity towards the water compared to sodium. Sodium has less negative electrode potential, and lithium, and another reason for lithium is lithium has smaller size as well as the maximum hydration enthalpy. And these alkali metals are also reacting with the proton donor elements like alcohols, alkynes and gaseous ammonia. Especially these alkali metals are showing reactivity towards the gaseous ammonia, not liquid ammonia. They will react with the gaseous ammonia. So this is about the reactivity towards water. And third property is the reactivity towards dihydrogen. Reactivity towards dihydrogen means hydrogen. So when alkali metals are reacted with the dihydrogen, they should form the corresponding alkali hydrides. So the alkali metals, when they are reacted with the hydrogen, they form the corresponding alkali metal hydrides. Okay, metal hydrides. And all the alkali metals ions are the alkali metal hydrides are ionic in nature, and they are having high melting point and high boiling point. All the alkali metal hydrides are ionic in nature. Because of this ionic nature, they are showing high melting point. Ionic nature, and these are existing solid form. Okay, because of solid nature, they will showing high melting point. So when they react with hydrogen, they form corresponding metal hydrides, and these will exist in ionic solid form, and they will exhibit the high melting point. So usually all alkali metals are reactive towards the dihydrogen. So next, the fourth property is reactivity towards the halogens. So similar to that of hydrogen, these are also reactive towards the halogen and form the corresponding metal halides. Solid in the previous property, when they react with hydrogen, they form corresponding metal hydrides. halogen, they should form the corresponding metal halides. Okay, metal halides. So Mh minus, the alkali metals, react with halogens, and forms metal halides. That is M plus X minus, corresponding metal halides. So if it is sodium, it will form sodium halide. So M is potassium, potassium halide. So M, if it is cesium, then it will form cesium halide. So halides may be chlorine, bromine or iodine. So in this way, radium shows reactivity towards the halogens. But lithium forms covalent compounds with the halogens. So when lithium reacts with the halide, it will form lithium chloride, lithium bromide, lithium iodide, etc. But those are covalent in nature because the lithium has the more polarizing capability. So polarizing capability is nothing but it will distort the electron cloud over anion. So see, for example, fluorine. So fluorine has 7 outermost electrons, means it has some electron cloud over it. So when lithium approaches to this fluoride, so this will distort the electron cloud over the fluorine. As a result of that, it will become polarized. So electron cloud, it will be distributed, or else it should be destroyed over the anion. So that's why the lithium has more polarization capability. Okay. Lithium halides are covalent in nature. And polarizing capacity depends upon the size of cation. As the size of cation decreases, the polarization capacity should be increases. If size increases, the polarization capacity should be decreases. But lithium is smaller ion compared to other alkali metals, so that is why it has maximum polarization capability, since it will form lithium halides. The form covalent in nature, it is because of high or more polarization capacity, high or maximum polarization capability. Maximum polarization capability. So this will distort the electron cloud over anion. So lithium has smaller size. Since it has maximum polarization capability. So this is the reason for the existence of lithium halides in covalent nature. So other than that, all the alkali metals are forming ionic halides, means they are in ionic nature, but except lithium. So lithium is showing covalent character when they react with the halogens because it has maximum polarization capability. So this is about the alkali metals. When they react with the halogen, they should form the corresponding metal halides. So next is the reducing nature of alkali metals. So this is the fifth property. So the alkali metals are behaving as a good reducing agents. So reducing agent means they will reduces others and but oxidizes itself. The agents which will reduces the other species but they should undergo oxidation cell. So those are said to be the reducing agent. So these alkali metals are showing reducing nature. So the alkali metals are strong reducing agents. Strong reducing agents. Lithium being the most and sodium is the least powerful. The standard electron potential which measures the reducing power represents the overall change. So the alkali metals are behaving as a good reducing agent. So the lithium is the best reducing agent, means it is showing more reducing nature compared to other elements, and the lithium is the stronger reducing agent compared to sodium. So sodium is the least reducing agent and it is depends upon the electrode potential which will measure the reducing power of elements. So in this way the alkali metals, so they should show sublimation enthalpy, ionization enthalpy as well as hydration enthalpy. So sublimation enthalpy is nothing but the amount of energy is required to convert solid molecules into gaseous phase, and ionization enthalpy is nothing but the amount of energy is required to remove the outermost electron from the metal. So in this way we will be removing the electron from alkali metals. As a result it will loses the one electron. Hydration enthalpy is nothing but the amount of energy released during the hydration of 1 mole of a molecule. So then the metal will become aqueous, so after hydration. So in this way these alkali metals are showing the reducing property. So lithium is the good reducing agent and sodium is, in case of alkali metals only I am comparing. So alkali metal sodium is the least reducing agent, and the last chemical property shown by the alkali metal is reactivity with the liquid ammonia. So next is the reaction with liquid ammonia or solution ammonia. So these alkali metals dissolves in liquid ammonia, and when they dissolves in the liquid ammonia they will impart blue color, means the solutions will become blue in nature and which are showing conductivity. So that's why the alkali metals when they dissolves in the liquid ammonia they are giving deep blue solutions which are conducting in nature. So this is the reaction. When alkali metals are reacts with the ammonia they form the corresponding ammoniated ions. So this ammoniated ion absorbs the light in the visible region. So that will be reason for the coloration of ammoniated solutions. So as a result of absorption of energy by that ammoniated ion, so that will give blue color. So as a result the alkali metals will become blue when they dissolve in the ammonia, means solution becomes blue, and upon standing they will liberate dihydrogen and they will form the corresponding amides. So these ammoniated ions slowly they will converted into amides, corresponding metal amides with the liberation of hydrogen, and these solutions the alkali ammonium solutions are paramagnetic in nature. So in this way, the alkali metals are showing different chemical properties with different elements like water. When they are exposed to air or oxygen, they will form out hydroxide. They are also reactive towards the halogens, and they are exhibiting reducing nature, and they are reactive towards the liquid ammonia. So these are the chemical properties of a liquid ammonia. So in next session we will discuss about the further. Thank you.